Welcome back. Last time we began discussing inverse functions and how to find them in some basic cases. Today let's start by discussing when we can find an inverse function. So let us consider a function f with f of x equals x squared. And if we don't write anything for the domain, we're going to assume that we're going to use the biggest possible set of real numbers that can be used as the domain. So I can take any real number and square it and get a definitive output. So we're going to assume the domain is the set of all real numbers, unless stated otherwise. Okay. If I make a table with some select values of the input, then -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. And for each of these inputs, I'm able to get a definitive output, no ambiguity. So this is a function. And we can say things like find f of 2. And that's when the input is 2, what is the output? Okay, so f of 2 equals 4. Okay. We can also ask things like, what are the values of x when f of x equals 4? Now notice last time I said what is the value. This case I've changed the wording slightly to what are the values, because I notice that f of x equals 4 occurs multiple times, right? So 4 is the output, and I'm looking for x, the input. So I see 4 here and here. So the input could have been -2, the input could have been 2. So I could answer x equals 2 or -2, and that would be a completely valid answer to this question. Okay. Now, when we talked about inverse functions, the deal was, if I write what is the value of f inverse of 4. So first of all, let's just pretend we can even ask this question. Okay. If we can ask this question, then that means take this, which is the input for the inverse, right? Since we're working back to it to switch the input and the output. So this would become the output of the original f function. And I'm supposed to figure out what the input of the original f was. Okay. Remember, because the input of the inverse is the output of the original, and the answer here, the output of the inverse, is going to be the input of the original, switching the input and the output, okay? So I'm looking for 4 as the output of f of x. But we've already discovered that there are 2 possible x values that we can use for the input. So the question, do we write f inverse of 4 equals 2? Do we write f inverse of 4 equals -2? Do we write 2 or -2? Oh no, this is ambiguous. And the rule with functions is that if it's ambiguous on the output, then it's not a function. So we would say, in this case, f inverse is not a function because we ended up in a situation where we got ambiguous outputs. So I cannot ask this, and I would end up saying that f inverse is not a function. So why specifically did that happen? It happened because there was an output value here that was produced by multiple different inputs. This characteristic, we say that f of x is not a one-to-one function. So what is a function? It is a set of instructions that takes an input and turns it into an output that is definitive, so this output is not ambiguous. And formally, we can say that if we have 2 values of x, x1 and x2, that are the same as each other, then a function f will take f of x1 and f of x2 and produce the same value every time. Okay. Then we ask, what is a one-to-one function? Well, it's a function that has unique outputs, meaning every output can only occur up to once. So above, this was a case where f was not a one-to-one function because the output 4 was not unique. The output 1 was not unique. It occurred for multiple x values. Formally, we can say this is if I have f of x1 equals f of x2, meaning there are two y values that happen to be the same. The only way that can happen is if the original x values were the same as each other. As in, if I have two different input values, I cannot get the same output value. Notice that this is just the converse of that. So this leads us to an important conclusion. We say that f of x has an inverse function, f inverse of x, if and only if f of x is a one-to-one function. Because if the outputs of f are not unique, when I switch the input and output, and I try to use the output of f as the input of f inverse, then I will get ambiguous outputs. Okay. So the immediate question that comes up is, how can we easily determine if f of x is a one-to-one function? Well, let's consider some graphs. So let's imagine I have a situation where let's imagine y and x have a relationship that are graphed in the following way. Okay. If I were to draw a graph that looks like this, and I ask, is this graph a representation of a function f such that y equals f of x, question mark. And of course, I can ask this in a simpler way, just, is this a graph of a function? Well, if I look at an input value of x right here, along this vertical line, I notice there are 2 points. So perhaps this might be x equals 3, and this might be 3 comma negative 4, and this might be 3 comma 2. Let's just imagine all of that. So if I asked, what is the value of f of 3? Well, if I could even ask this question, that would mean for the input value of 3, which means x equals 3, I would go and try to find y as the output of f of x. Well, that could be 2, or it could be negative 4. So do I say this is 2? Do I say this is negative 4? Do I say it's one or the other? This is ambiguous, so I cannot ask this question. So we'd argue that this cannot be the graph of a function with f of x equals y. This is what we call the vertical line test, where if I draw a vertical line and it intersects multiple locations on the graph, then I would say the outputs are ambiguous for a given input. So this cannot be the graph of a function. Okay. So let's imagine a case where we pass the vertical line test, meaning we can draw any vertical line and it will only intersect the graph at most once. So let's consider something like this. So if I consider the vertical line test, I can think from the left, if I have a moving vertical line, I never intersect the graph more than once for every vertical line. So this can be a representation of a function y equals f of x. Okay? So now I can ask the question, is this graph a representation of a one-to-one function f such that y equals f of x, question mark. Well, remember what a one-to-one function is. It means that the outputs have to be unique, which means for every output that is a y value, I can only have up to one input value that creates that output. So let's imagine I pick a value y that is, let's go with y equals 1, for example. So let's just make up some points. This looks like 0, 1. Maybe this is negative 2, 1. And maybe this over here is 5, 1. Okay? So we notice that there are multiple inputs, negative 2, 0, and 5, that all are going to produce the same output, 1. We can say f of negative 2 equals 1, f of 0 equals 1, and f of 5 equals 1. So that means this is not the representation of a one-to-one function, because we have discovered that the output 1 is not unique. In this case, we drew a horizontal line. So we call this the horizontal line test. And we say, okay, if you draw a horizontal line and it intersects the graph multiple times, then you have failed the horizontal line test, and that graph cannot be the graph of a one-to-one function f. Vertical line test to check if the graph is of a function, horizontal line test to check if the graph is of a one-to-one function. And keep in mind, f of x has an inverse function if and only if it is a one-to-one function, which means, in this case, f is not even a function. In this case, f is a function, but it does not have a valid inverse function. Now let's go back and consider the f of x equals x squared function we had earlier. So we see that the graph of y equals f of x fails the horizontal line test. If you draw a horizontal line, it intersects the graph in multiple locations, which means for that output, there are multiple possible inputs, meaning the outputs are not unique. Okay? But what if I place a restriction on the domain and say I'm only going to allow x to be bigger than or equal to 0, which means I'm only going to allow this part of that graph. So if I were to erase this and look at just that, now we notice that this graph passes the horizontal line test. This function, with a suitable domain restriction, is now a one-to-one function. Okay, so we can ask the question now, how do we find f inverse? Well, we did a lot of this motion last time where I said switch the output and the input. And so one of the ways to find a function rule for the inverse was to say, let's write down the original as y equals x squared. So I'm putting y instead of f of x. And we're going to switch the x and the y. So I'm going to cross this out and write x in place of the y and y in place of the x. And keeping in mind, of course, we have this new restriction that originally x had to be bigger than or equal to 0. So when we switch the x and y, we've switched the symbols. So we've acquired the restriction that y has to be bigger than or equal to 0 in this switched case. So I want to solve for y. If I square root both sides, remember that we end up with a plus or minus both possibilities. But because y is bigger than or equal to 0, I cannot have the negative version, because a square root of a real number will always produce a 0 or positive real number, which means if I only want 0 or positive outcomes, then I cannot accept the negative right here. So my conclusion will be that f inverse of x is the square root of x. Now, what if I had done it slightly differently? For example, what if I consider g of x equals x squared plus 2? And I'm going to consider this with the domain restriction x is less than or equal to 0. And it turns out with this restriction that we're going to get a one-to-one function for g of x. Okay, let's find g inverse of x. So by the same method, we're going to first write down y equals x squared plus 2 with the restriction that x is less than or equal to 0. And we're going to switch the x and the y. So we're going to write x in the place of y and y in the place of x. And now the restriction is going to apply to the y variable. I'm trying to solve for y, so I'll subtract the 2, x minus 2 equals y squared. And then I'll square root both sides, which will produce plus or minus x minus 2 is equal to y. But since y must be less than or equal to 0, and taking a square root will produce a result greater than or equal to 0, if I accept the positive outcome, then my outcome will not be matching the y is less than or equal to 0 condition. So I cannot accept the positive version. I must accept the negative version here. So I will conclude that g inverse of x equals the negative square root of x minus 2. So now a meaningful thing we can do is to consider the graphs of the inverse functions. So let's, on the calculator, pull up a graph page. And let's say our f of x function is x squared. So that's going to be our original parabola. But if we want to place a restriction on it, what we can do is we can use, if I hit Control equals, it pulls up the logical symbols. The vertical bar is such that. So I want x squared such that, and I can place the restriction, x is bigger than or equal to, once again using the logic symbols, 0. And if I do that, it will give me only the right half of that parabola. Okay. Now, if I want to graph f inverse of x, well, then I can just say this is the square root of x, and that will be the f inverse. And notice what's going on here. It looks like I've sort of flipped in some interesting way. Okay. So keeping in mind that I am switching the x and y values because what used to be the y value of the blue graph that was the output of f is now becoming the input of f inverse, so it's becoming the x value of this graph. So the x and y are switching. And just for fun, we can check this out with the graph trace tool, where we can say if I go to trace, graph trace, and let's imagine, so I'm on the blue graph, let's plug in a number for x. Let's imagine 2.5. So we're going to get 2.5 comma 6.25, which means f of 2.5 equals 6.25. Now, I want to switch the x and the y and look at when x is 6.25 on the red graph. So if I hit the up button, then I switch to the red graph. And if I type in 6.25 for my x, it's a little bit hard to see here, and I hit enter, I get 6.25 for the x and 2.5 for the y. So at least in that example, x and y are indeed switched, and hopefully you agree with me philosophically that the x's and y should be switched for all the values on these two graphs. So now, what if I were to graph the y equals x line, so f of x equals x? Now notice that cuts right through those two graphs, and there's some interesting symmetry going on here. And this is indeed what's happening. If you switched the x and y coordinates in the graph, that is geometrically equivalent to reflecting the graph over the y equals x line. And that's why we teach that to get the graph of an inverse, all you do is you take the original graph and you take the y equals x line and reflect the graph over that, and you get something like this. Okay? Now, what if I want to do the same thing down here? So first of all, I need to know what the graph of this looks like. So why don't I ask the calculator to do that for me? So I will delete this. And in here, we will say x squared plus 2 with the restriction that x is less than or equal to 0. So we see that is the graph of g of x. And if we want to graph the inverse, which we already know is negative square root of x minus 2, we see it over here. And we see that the blue graph reflected over the y equals x line produces the red graph. The x and y values are switched. So for our final point of discussion today, let's talk about the domain and range of a function and its inverse. So we had g of x equals x squared plus 2 with the domain restriction x is less than or equal to 0. And we found that g inverse of x was equal to the negative square root of x minus 2. Now if we ask the domain of g, then we would say, well, we have been given the restriction that the input must be less than or equal to 0. So we can say all the inputs fall into the interval from negative infinity to 0, and then bracket to include the 0. And the range of g, keeping in mind that ranges are a little bit harder to find, so you either have to logic your way through the function, or you can look at a graph. And if we can look at the graph on the screen, we see that the y values start at 2 and go up. So we can comfortably conclude that it's from 2 to infinity, including the 2. And then if we look at that red graph, okay, what if I ask for the domain of g inverse? Well, the x values on this graph start at 2 and go all the way to infinity. So that would be from 2 to infinity. And the range of g inverse would be the y values on the red graph. So it looks like it starts at 0 for the y and then goes down forever. So we would say that's everything less than or equal to 0. So in interval notation, that's from negative infinity to 0, including 0. So notice what happened here. The domain of g matches the range of g inverse. Then the range of g matches the domain of g inverse. Oh, but of course, because we're switching the input and the output, so the input, which tells us the domain of g, is going to become the output of g inverse, and the output of g, which gives us the range, is going to become the input of g inverse. So when you find the inverse of a function, you are switching the x and y values, switching the input and output. You're also switching the domain and range. So that might be an easy way to decide how you should select plus or minuses, or perhaps some other restrictions that you need to impose on the inverse function once you know the domain of the original function. Now let's just do a quick recap. So a function takes an input to an output, but it needs to be a definitive, non-ambiguous output. Okay, so we need unambiguous output. What does that mean in a graph? It means it passes the vertical line test. Okay. To be a one-to-one function, that means it needs to produce a unique output, which means you cannot have the same output occur multiple times for different inputs. Okay. That means it must pass the horizontal line test on the graph. And the deal was, if you are a one-to-one function, then you can have an inverse. So we say f of x has inverse function, f inverse of x, if and only if f is a one-to-one function. Okay, now the next question is, how do we find an inverse? Well, what we do is we switch the x and the y. So we can imagine this as switch the input and output. So if I were to write this as f of x equals y, so I can say if f of x equals y, then f inverse, I would use the output here as the input there, and say this is x. Or I can imagine this as switch the x and y coordinates on the graph, right, which is the same thing as reflect the graph over the y equals x line. And the third thing that shows up is I'm going to switch the range and the domain. So the domain of the function f is the same thing as the range of f inverse, and the range of the original function f is going to become the domain of f inverse. And there we have it. That's the theoretical overview. Now hopefully we'll do a few problems, and you'll get a more tangible sense of how to deal with these things. Thanks for tuning in. I'll see you next time.